Welcome you all to Principles of Organic Synthesis. At present, we study aromatic diazonium salts. In this topic, so far, we had 2 lectures. The first lecture, we saw the preparation of diazonium salts, the possible reaction mechanisms for the reaction of diazonium salts with nucleophiles, where we have seen 3 types of mechanisms. The first one, the nucleophile can undergo addition reaction with this nitrogen of diazonium salt, will get the addition product, where we have seen the reaction of cyanide ion and phenoxide. Then we have seen the reaction that involves carbocation intermediate. For example, if we take the diazonium salts and warm it, it can release nitrogen and produce aryl carbocation, which can readily undergo reaction with the nucleophile. We have seen some examples. Then we have seen the reaction that involves radical intermediate. If we have aryl diazonium salt, for example, when you react with copper 1 halide, it can reduce the diazonium salt into aryl radical by single electron transfer process. Once we have the radical that can further undergo reaction, we have seen, for example, Sandmeyer reaction. The lecture 2, next we have seen the reaction of aryl diazonium salts that can be replaced by aromatic hydrocarbon. For some, we have seen some examples where you can try to construct polycyclic aromatic compound like phenanthrene. Then we also have seen the coupling reactions with amines, phenols. Then also we have seen the reaction with beta-keto ester. Depends upon the nature of the beta-keto ester, you can convert into the corresponding hydrazone. Following that, we have seen the reaction of amino alcohols. For example, if you have the cyclic amino alcohols, that you can convert into diazonium salt. Once you form the diazonium salt, if the nitrogen is present, the alpha carbon with respect to the hydroxy group that is bonded to the carbon, then it can undergo ring expansion to give the ketone as the product. We have seen some examples. Today we will continue the reaction of diazonium salts. The first example what we are going to see today is the synthetic use of diazonium salts for the formation of dyes. The first example you can see here, it involves reaction of this diazonium salt with this naphthalene oxide. It can undergo addition reaction to get this para red. This we use to make color of the wool and paper and many other materials. And if you look at this reaction, already we have seen, and the preparation of this diazonium salt can be carried out. For example, if you have aniline, so you can try to convert into para-nitroaniline. First you have to react with acetic anhydride, then you will be able to have acetanilide. Once you have this one, you can do the nitration. You will be able to get a mixture of para and ortho product. This is to be major compound. You can separate them out. Once you separate this one, you can do hydrolysis. To get para-nitroaniline. Once if you have this one, when you react sodium nitrate H2SO4, and then you can make the corresponding diazonium salt. Just as we have seen, if you have this anion which can now undergo addition with this nitrogen, then you will be able to get the addition product, and it can exist mixture of trans and cis forms. And once if you have this one, now this is the color of this dye is red, so we use the wool industries to make color of the class C. What you have to do here, basically in this dye, and they react the cotton wool with this one of them, then they add this one. Basically the dye is made in situ. On the wool they take in this one of the salt, then they add the another one, the dye is made and in situ. In this way we can make color of the wool. The next one is, if you look at here, this is known as neutral dye. The other one, you can see here similar reaction. In place of nitro group, you can also have a sulfonic acid functional group. This also can undergo reaction similar way, then you will be able to get this dye. The color of this is orange. So when you replace this nitro to the sulfonic acid, you can see here this is red, this is orange color, and this also can be made if you have aniline. You can react with sulfuric acid, you will get the salt. When you heat it at high temperature, you can lose water and then rearranges to beta-amino benzene sulfonic acid. So once we have this one, as just we have seen, and you can try to react with the nitrous acid in acidic medium, you can make the diazonium salt. Once we have this one, this can undergo addition reaction, as just we have seen, you'll be able to get this dye which is orange colored. And this since you have the acidic functional group, so this is known as acidic dye, and this dye also we use for coloring materials like paper, wool, and several applications they find. And if the difference between them is, and you can make the dye, you can add it to the wool, because you have the sulfonic acid, we can strongly bind with your wool. But in this case, and you have to they usually make in the situ, and then they make the color. But in this case, you can make the dye and add it to your wool, and it can strongly bind with your wool. And this way, this is the color of this dye is orange. The next application is you can see here we have seen two dyes so far. The first one is neutral, second one has a sulfonic acid functional group, so therefore we call it as acidic dye. The next one, look at here, this 2,4-thiaminotoluene here, you can see here. Once we have this one, and this can undergo addition reaction. So once we have this one, you can also make the corresponding diazonium salt. And this, now look at here, and this position is active because you have this ortho to this amino group, and if you compare with methyl, amino group is more activating group, therefore, and this the reaction takes place in this carbon. So you have to take 2 equivalent of this diamine and with this diazonium salt. So you need 1 equivalent of this. When you mix this one, and this can undergo addition reaction this carbon, and you will be able to get this compound. You can look at here, and so 2 molecule of this, the blue color is here, and 1 molecule of this diazonium salt, they can undergo addition reaction. You have the 2 diazonium functional group, so you can undergo addition here, then you will be able to get this dye. If you look at here, you have the amino group. 4 amino group in this, therefore is known as basic dye. And this is, you can see here, it is has a brown color. This also we use in the industries to color the material. For example, nylon and many other material are made colored using this dye. And this also you can, how will you make this one? This you have toluene is available. Once you have the toluene, you can do the nitration. So you get first the para nitration takes place, then it can undergo further reaction with this one. This then you have, with respect to the meta, with respect to ortho, so you can get this dinitrotoluene. Once we have this one, you can try to reduce. To the corresponding diamino derivative. Once if you have this one, this, so you can also you can try to react with the nitrous acid as we have seen earlier, and controlling the temperature you can make the corresponding diazonium salt. So then once we have this one, then it can undergo addition reaction, then you will be able to get the dye. The next one, if you look at the previous 3 dyes, one example we have seen for the neutral dye, one example for the acidic dye, another example for the basic dye. This one, if you look at here, here the reaction of salicylic acid with this diazonium salt is shown here. As just we have seen, it can undergo addition reaction. If you look at here, and this carbon is para to this phenoxy group, and this is meta to this carboxylic acid. Therefore, this position is activated now, which can undergo addition reaction. Then you will be able to get this compound. Once if you have this one now, so you can now introduce, for example, in this case they have introduced aluminum 3 salt, which can chelate with your dye as well as wool. So in this way you can color the material, and in the place of aluminum, chromium also often used. And here the use of aluminum demonstrated. This can link with your wool. In this way you can color the material. This is known as alizarin yellow, or you can see the color here, yellow color. This is a brown color. We have seen 2 examples, one for orange, another one for red. So similarly, diazonium salt finds broad utilities to make dyes, which we often use to color the material. Here the application for the indicators are shown. The first example involves when you have the anthranilic acid, already we have seen, you can try to react with the nitrous acid in acidic medium, and you will be able to form this diazonium salt. Once if you make the diazonium salt, which can undergo addition reaction, as we have seen earlier, here the reaction of dimethyl shown, the reaction will take place at the para position, addition reaction, you will be able to have this intermediate. So this is known as methyl red, and this red color one, and this we use as pH indicator. Suppose when you carry out the reaction, the pH of the reaction medium is this one, 4.4 to 6.2, you will get this compound will show red color, and this if acidic, and as you can see here, it can go here and this can come here, it can form. This can also use so it can go back. So it depends upon the pH of the reaction you can get. So when you have the range between 4.4 to 6.2, you get red. So this basically we use as a pH indicator. The next example is methyl orange. This also we use as an indicator already know that we methyl orange we use as indicator during the titration. If the reaction medium is acidic, you shows red color. If it is basic, you will see the yellow color, and this can be made from aniline, as we have seen. If you have the aniline, and when you react with sulfuric acid, so you make the salt, so this when you heat high temperature, it can lose water molecule and will be converted into once you form this one, then you can react with the nitrous acid and you can make the diazonium salt. Once you have this one, as just we have seen, it can undergo addition reaction, then you will be able to get this dye. If you look at here, the difference between here and you have, this is same in both case. One you have here carboxylic acid group in the ortho position, in another one you have the sulfonic acid. Both we use as indicators to check the acidity of the reaction medium. Now let us look at application for the synthesis of substituted aromatic compounds. For example, the reaction of naphthol is shown here. When you have the naphthol, you can try to react with this phenyl diazonium salt. Here the reaction will take place in this carbon, which is activated, as you can see here, and it can undergo addition reaction and you can get this addition product. Once we have this one, you can try to reduce using Na2S2O4 and it can reduce into amine, and this you can, in this way you can try to prepare 4-amino 1-naphthol as a product. The second example involves again the reaction of here 2-naphthol with this same diazonium salt. When you react with phenyl diazonium salt, here this portion is activated, it can undergo addition reaction. Already we have seen several examples. Once if we have this one, as just we have seen above, you can try to reduce, you can get this 1-amino 2-naphthol as a product. Once you form this one, and this can be further oxidized using FeCl3 in the presence of oxygen, you will be able to get quinone as the product. So as you know, diazonium salts find wide applications, not only to make dyes, you can also use as precursor to make variety of substituted aryl derivatives. The next example involves application of diazonium salt in medicinal chemistry. Now let us look at this substituted phenol derivative. Once if we have this one, this can be converted into this drug thymoxamine, which is widely used in urology. And so now let us look at how the diazonium salt is involved in the synthesis of the drug. This is the starting material. Once if we have the starting material, so you have to product with the amino group, where you have to convert this to ester, and this side you have to make the ether functional group. And when you react with acidic anhydride, it can undergo acylation. You get this amide. Once if you have this one, now you can try to react with the base. This is commercially available. Once if you have this one, it can undergo, you can convert into, and you will get this once we have this one, this also you can deprotonate. So this also can exist in the form of unolate. Once if we have this one, this can now undergo reaction, SN2 reaction in the presence of base, and so you will be able to get. So this derivative, once we have this one, you can do one make salt and do hydrolysis, then you will be able to get preamine, and as the product, once we have this one, now you can make diazonium salt. You can try to react so you have to, as we have seen, you have to maintain the temperature 0 degree. You can make the corresponding diazonium salt. You have this salt. Once we have this one, you can try to react with water. When you heat it, you can make carbocation which can react with water. You will be able to form this phenol. Once you have this one, now you can try to react with acidic anhydride in the presence of base, and you will be able to form this is a drug. So you can see here the diazonium, you form the diazonium salt as intermediate, which is further reacted, converted into phenol, which is further acylated to give this drug. And so you can see, as you can see here, diazonium salt find broad utilities, not only in synthetic chemistry, we also use as in medicinal science to make medicinally important compound. An example shown here. Now let us go for the recent applications of diazonium salts. Here an example shown for the CC coupling reaction. This is, you can see here the coupling of this diazonium salt with this boron derivative shown here. In this way you will be able to make the biaryl system. So all of you know Suzuki-Miura coupling reaction, and where already we have studied if you have the aryl halide, for example aryl bromide, you can try to react with boronic acid. If you have this one, you can try to react with boronic acid in the presence of palladium 0 and base. For example, if you take sodium methoxide, you can convert into So in this way you will be able to make biaryl. Already we have seen in this reaction, if you remember, the palladium 0 undergoes reaction with this aryl halide. Now let me write here like this, AR. So once if you have this one and the palladium 0 is involved, it undergoes oxidative addition, you now will have this palladium 2, which is further reacts with the base. For example, if you use sodium methoxide, you will end up with, and you will lose sodium bromide. Once you have this one, this can react with boronic acid through transmetallation. If you have the boronic acid, you can react with sodium methoxide and you will form eight complex. So this can now undergo reaction, and what you will form? You will form now if I write this one, then already this will be AR, and this side you have the phenyl, you have now palladium 2. This can give the product by reductive elimination. So in this way you will be able to make the biaryl system. Here this is crucial, you have to add a base. This is very crucial in the Suzuki-Miura coupling reaction. You can see here you don't need base, and using diazonium salt you can try to couple the boron derivative using palladium charcoal in methanol solvent at moderate temperature. In this way you will be able to get the biaryl system. As you can see here, you can try to couple a variety of functionalized systems. For example, you can have the aldehyde group, you can also have halo substituent, they readily undergo reaction. You can see here the yield is very good. The next example, also the reaction of boronic acid with the diazonium salt is shown here. You have the aniline, which can be reacted with this organic nitrite in the presence of acetic acid. You can make the corresponding diazonium salt. Once you make the diazonium salt, and this can be coupled with this boronic acid using this palladium catalyst in the presence of the phosphine ligand, and in this way you will be able to make again a biaryl system having different functional group. You can see here. So if you remember, we have seen that when these diazonium salts are not stable, you have to make the reaction medium, you have to carry out the reaction. However, when you have this diazonium salt using organic nitrite and acetic acid medium, you can try to precipitate out using ether, and you can use for various applications. This is one of the example here. When you react with this organic nitrite and the presence of acetic acid, you can get the isolable diazonium salt, which can be used for the coupling reaction. The mechanism of the latter reaction shown here. When you react aniline here, you can make the corresponding diazonium salt, as you can see here, and using this organic nitrite, you can get this acetate salt. Once we have this one, now you have the palladium 0, which can undergo reaction. You will get this intermediate, palladium 2 intermediate. Once we have this one, this can lose nitrogen. You will be able to have this salt. This salt now can undergo reaction with the boronic acid. You will be able to have this intermediate. Once we have this one, this can give the product by reductive elimination. You regenerate the catalyst. So if you compare the, just as I mentioned, the Suzuki-Miura coupling, where you need base, you don't need under these conditions. You can make the diazonium salt, which can be readily reacted with palladium 0 salt in the presence of ligand, appropriate ligand, and the reaction can be accelerated, you will be able to form a palladium 2 system which can be converted into the biol product by reductive elimination to regenerate the catalyst and complete the catalyst cycle. The next example is Heck-Matsuda reaction. As all of you know very well, Heck reaction you know very well. If you have the aryl halide, for example, bromobenzene, and if you have, for example, any alkene which has electron withdrawing group, it can undergo addition reaction using, already we have seen palladium 2 acetate and phosphine ligand. You have to use substituted phosphine ligand and the presence of base, and in the atmosphere you can try to this already we have seen. This also involves zero oxidation state. As we have seen, palladium first is reduced by the ligand, you have the 0. Once we have this one, and when you add aryl halide, it can undergo oxidative addition. You will have once we have this one, now this can react with our alkene. So this now convert into X. Once we have this, it can rotate. Once we have the hydrogen syn transition state, then it can undergo isomerization, and then the beta hydride elimination can lead to the formation of the styrene derivative. And once we have this one, this can now the presence of base under reductive elimination. So you have the base and it can be removed by base, and then in this way you can complete the catalysis. This what the reaction mechanism, catalytic cycle of Heck reaction. Here you can use the diazonium salt in the place of aryl halide, which can undergo addition reaction as we have seen. And here you see, here you don't need any phosphine ligand, and you carry out the reaction methanol at room temperature. You can try to get the coupled product. But if you see the traditional Heck reaction, you have to heat the reaction. You have to carry out around 100 degrees Celsius in DMF solvent under inert atmosphere using phosphine ligand. Here you can readily react this diazonium salt with this styrene derivative at room temperature to give this CC coupled product. So here an application shown, and you can just as we have seen, you can try to react this aniline derivatives with this organic nitrite. You can make the corresponding diazonium salt, which can be reacted with palladium acetate and methane sulfonic acid, and it can undergo addition reaction. You will be able to get this compound. Once this has been further converted into this lactam as a product in a high yield, as you can see here. Therefore, if you have the diazonium salt, which can be readily reacted in the presence of palladium based catalyst system for the CC coupling reaction. In this way, if you have, for example, here the reaction of methyl acrylate with this aniline derivative shown, you can couple them, you will get this cinnamic acid derivative as the product. So far we have seen the CC coupling reaction using diazonium salt as a precursor. First we have seen the reaction with boronic acid. Then we have seen some example for the Heck reaction. Now let us look at the photocatalytic arylation of alkenes, alkynes and enones. These are some of the recent developments in this diazonium salts chemistry. And you can see here, for example, this diazonium salt can be readily reacted with styrene and using this photocatalyst and to give the coupled product. Just we have seen, you can carry out the reaction using, if you, for example, if you have the methyl acrylate, you can try to couple diazonium salt with vanadium based catalyst. However, if you use, you can also try to couple, for example, in this case, this diazonium salt can be readily coupled with this styrene using the ruthenium based photocatalyst. At room temperature, you can couple the, you can get the CC coupled product. In this way, you can make the trans-trilbene, substitute a trans-trilbene as a product. So if you have the styrene, you can couple with the variety of diazonium salt, you can get the substituted trans-trilbene as the product. The next example involves the reaction of coupling of diazonium salt under photocatalytic conditions. You can also couple with the alkyne, and in this way you will be able to make the substituted alkyne. And the next example shows the reaction of enone. You have the enone which also can be readily coupled. In this way you can do the arylation reaction using photocatalytic systems. This is some of the recent developments in the, as I mentioned, the diazonium salts chemistry. All of you know very well, if you want to couple terminal alkyne, if you have the aryl halide, you have to use Sonokoshira coupling condition. What you have to do, you have to, if you have the aryl halide, for example aryl bromide, you can try to couple with, say, terminal alkyne, for example this one, using so at moderate temperature. This is a very standard condition if you want to couple using aryl halide with terminal alkyne. So in this reaction, as you know very well, this also involves palladium 0. You have the palladium 0 which can undergo reaction with your aryl halide. Let me write like this. You will be able to get this addition product through oxidative addition. Once we have this one, now it can undergo, so you have the alkyne in the presence of base. Form this species when you have the alkyne. The hydrogen iodide, whatever you generate, will be trapped by base. You will have this one. This can undergo now transmetallation. So this can give the product by reductive elimination. To complete the catalytic cycle. But if you look at here, you can carry out the same reaction using the diazonium salt and terminal alkyne using the photocatalyst at room temperature, and you can get this substituted alkyne as a product. Here an example shown for further for the Sonokoshira reaction, as just we have seen the mechanism for the reaction. So usually Sonokoshira reaction is carried out using tetrahydrous triphenyl phosphate palladium as catalyst in the presence of copper iodide and diisopropylamine as the base at moderate temperature. You can carry out the same reaction here using this diazonium salt and this alkyne using palladium 2 chloride, and so here AuCl and catalytic amount in the presence of this heterocyclic carbene, and you can carry out the reaction at room temperature. In acetonitrile solvent you will be able to get the substituted alkyne as a product. Another example shown here similar to here, this palladium 2 chloride has been used in the presence of copper iodide and tetrabutyl ammonium iodide and diethylamine. At room temperature you can make the substituted alkyne as the product. So far we have seen some examples for the Sono-Koishira coupling reactions, and now let us look at the direct CH relation. In an example shown here, if we have this diazonium salt, and this can be in the presence of palladium 2 catalyst and this photocatalyst, and you can try to do the direct CH relation. In this way you can make CC bond formation. This some of the example you can see here, and you can make the biaryl systems. The mechanism of this reaction shown here, as just we have seen, so you have this ruthenium bipyridine complex which we use as photocatalyst, and the presence of light it can convert into the cation radical. Once we have this one, this can reduce this diazonium salt into aryl radical, where you produce nitrogen as a byproduct. You generate the tetrafluoroborate, and where this is converted into ruthenium 3. Now this aryl radical, now you have the palladium 2. The palladium 2 what you have here, the palladium 2 can now react with the aryl radical, you convert into palladium 3, and this can now reduce the ruthenium 3 to ruthenium 2, and palladium 3 will be oxidized to palladium 4. Once we have this one now which can react with your substrate, and you can form the arylation product where you generate H plus, and where this can be converted into reduced into palladium 2, and this how this you can see here, this involves the combination of palladium 2 acetate as well as photocatalyst. In this way you can try to couple diazonium salt directly with the aryl CH bond. In this way you will be able to make biaryl systems. The next example involves the use of organic dye, and the earlier example we have seen the use of ruthenium based bipyridine complex as photocatalyst. Here the use of organic dye, US in Y is shown here. This also can be used as catalyst, photocatalyst to coupling of the diazonium salt. Here the reaction with the furan is shown here, which can readily couple here. In this way you will make this coupled product, CC coupled product, via direct CH relation. Now let us look at the mechanism of this reaction. So you have here your dye, which can, the presence of light can be converted into this one. Once we have this one, this can reduce. It can transfer electron to the salt, diazonium salt, where it will be converted into this radical nitrogen and tetrafluoroborate. Once we have this one, this can, the radical cation can be now reduced by the substrate, as you can see here, then to regenerate the catalyst. Now the radical can react with the substrate, it can undergo addition reaction, as you can see here. So now this can react, and we will have this radical. Once we have this one, this radical, this can reduce this cation radical to the catalyst, which will be converted into cation. Once we have this one, this you have the tetrafluoroborate, it can cleavage of the CH bond can give the CC coupled product. Alternatively, this radical also, whatever you have the radical, which also can transfer one electron to this, it can reduce the diazonium salt In this way it will be converted into the radical, and it will be converted into this cation intermediate, which can in the presence of tetrafluoroborate can be converted into this compound. There are two possibilities you can see here, and so this another example. You can use organic dye as photocatalyst to couple diazonium salt with aromatic systems. In this way you will be able to form CC coupled product. The next example involves the reaction of this diazonium salt with alkyne, and so we have seen earlier the coupling of terminal alkyne, Sono-Koshira coupling reaction. Here the reaction of disubstituted alkyne is shown here. This also can be carried out with the diazonium salt as shown here. When you react with this one, and you will be able to so as we have seen earlier, when you take the diazonium salt, which can readily react with the palladium 0, you get the palladium 2, this salt. Once we have this one, which can now react with this alkyne through addition reaction, as you can see here, insertion reaction, you will get this one. Once we have this one, this can react with another molecule of the alkyne as shown here, which can undergo cyclization. You will get this cyclic system. Next one is the reaction of this nitrodiazonium salt. In the presence of FeCl2, it can convert into the corresponding radical, which can undergo dimerization. In this way you will get the biphenyl system. The reaction mechanism shown here, and the Fe2 is can transfer one electron to the diazonium salt, where it will be oxidized to Fe3, and you will have the radical. Once with this radical, this can undergo dimerization to give the CC coupled biphenyl derivative as the product. So the next reaction involves the coupling of diazonium salt with the styrene using the radical initiated tempo to give this addition product, as you can see here. And so this reaction involves a radical pathway. So the mechanism of this reaction shown here, the diazonium salt can be reduced to the radical by single electron transfer process from the salt. Once you can convert into the phenyl radical, and you will have the tempo. Once we have this one, now this can undergo addition reaction, and you will have this radical. This radical can be trapped by tempo. This way you will be able to form this addition product. This clearly shows that the reaction involves a radical pathway. So whenever you have this tempo derivative, you can try to react with the diazonium salt, and it can convert the diazonium salt into aryl radical by single electron transfer process, and which can readily undergo reaction with this styrene to give this addition product radical. This radical can be trapped by tempo to give this derivative. So far we have seen the CC coupled product. Now let us look at the coupling of boron derivatives. Here the reaction of this diazonium salt, this phenolchalporine shown here, which can be coupled using copper bromide to give this derivative. And similarly here the reaction of this diazonium salt has been shown using this eosin dye, and which involves a photocatalytic reaction. In this way also you will be able to the CB coupled product. So which are important starting material, the cross coupling reactions. You can see here, usually if you have the aryl halide, you have to react with butyl lithium. You have to make the lithium reagent, then we react with the boron derivatives. Here you can see here, and you can try to directly react the diazonium salt with this phenolchalporine. You can, the presence of photocatalyst, you will be able to make the boron derivatives. In summary, so in this class we have seen how the utilities of diazonium salt in the preparation of dyes, where we have seen four types of dyes. First we have seen the formation of neutral dye, which is used to color the wool, and this dye is made in situ. So the next we have seen the dye that has acid and base functional groups. Then we have seen the dye that has aluminum metal, which is making chelation with this dye and the wool. And then we have seen the utilities of diazonium salts for the preparation of indicators, and we use as a pH indicator. Then we have seen the application of diazonium salt for the synthesis of a drug molecule, which we use widely in urology. We have seen one example. Then we have seen some examples for the organic transformations. We have the azo compound, diazo, which can be readily reduced using Nu2S2O4. We have seen some example you can convert into aniline, which can be further converted into useful compounds. Then we have seen the recent developments for the construction of carbon-carbon boron bond via cross-coupling reactions. We have seen several examples using transition metal based CC coupling reaction as well as using photocatalytic systems. These are some of the recent developments. In this way, you will be able to utilize the diazonium salts to convert very useful compounds. So as you know, if you look at all these three lectures so far we had, you can clearly note that diazonium salts has broad utilities in the synthetic chemistry. They are easy to prepare. Once you form, you can use for variety of applications. With this we conclude this lecture. Thank you very much.